All right, for the benefit of those of you that could use a little bit more instruction on this problem, I'm going to work through each step of this problem. I'm going to remind you that for this problem, the main thing that you need to do first is recognize that you need the molar mass of this benzene, this C6H6. We can calculate the molar mass by simply taking the number of atoms of each element in the molecule, finding their molar mass from the periodic table, and multiplying their molar mass by the number of that element. So what I've got written out here is 6 times 12.0107 grams per mole, because this is the mass per mole of carbon, and in 1 mole of this compound we've got 6 moles of carbon. That's what the 6 is telling us. If there's 6 atoms of carbon in 1 molecule, that means there's also 6 moles of carbon in 1 mole of this molecule. And so since we're trying to solve for the molar mass of the molecule, which is the mass per mole of this compound, then we want to be solving this for 6 moles of carbon and 6 moles of hydrogen. So over here on the other side, we've got 6 times the mass of hydrogen. And I apologize for, I'm using a periodic table here, or this key I should say is from using a periodic table that had slightly more sig figs on the molar mass values in the periodic table. So just keep in mind the periodic table I provide you guys with, this would have been 12.01 and this would have been 1.01 over here. So you might get a slightly different number for the molar mass if you're using our periodic table, but the process is still exactly the same. So next we are going to use this molar mass to convert the grams of benzene into the moles of benzene. And we can do this by recognizing that this unit here for molar mass, grams per mole, that's a compound unit, which is basically telling us the number of grams of the whole compound per 1 mole of the whole compound. So notice that molar mass can be written as a conversion factor between grams and moles of a compound, and that, remember, conversion factors can be written either direction, right? So either we can have the grams on the top and the moles on the bottom, or we can have moles on the top and grams on the bottom. And I'm realizing that the way I wrote this might be a little confusing because I didn't put the actual number in here because I was just trying to show how the units line up. But keep in mind here that this would be this 78.11184 grams that we see here. That whole thing would be on the top. And then you assume that there's 1 mole when you see per mole in a compound unit like this. So to get the moles, we are starting with the 4.24 grams of benzene, and we're using the molar mass as a conversion factor to convert grams into moles. And notice here that I did flip the orientation of this conversion factor, because if I'm starting with grams of C6H6 and I want to cancel out grams, then that grams of C6H6 needs to be on the bottom, and on top I want to have moles. So notice here that this is actually writing the molar mass, the 78.11184 grams on the bottom and the 1 mole on the top. And again, that's so that our units are going to cancel out correctly and we're going to be left with moles, which is what we want to solve for here. So notice this is the same as dividing by the molar mass, but it's always good to make sure you understand how to do this or how to set this up with a dimensional analysis style approach. So the answer we're going to get when we type this in is 0.0543 moles of C6H6. And so that's coming from taking the 4.24 grams and dividing it by the 78.11184 grams. So this conversion that I just did is an example of a grams to moles conversion. And so notice, in order to do a conversion from grams to moles, remember these arrows in my roadmaps always represent conversion factors. And so molar mass is the conversion factor we need when we go from grams to moles. This also means that if you're ever given the number of moles and asked to solve for the number of grams, you use the same conversion factor. You use the molar mass to go from moles to grams. So this will work either direction. You just have to be careful about the way that you set up the conversion factor. Obviously, going from moles to grams, we would actually be using this original way that I wrote this molar mass as a conversion factor, because moles to grams, we would want to cancel out moles and we would want to end up with grams. So that is how that's going to work. So moving on to total number of molecules of benzene, I encourage you for all of these problems to think about how you would start with grams and go all the way through to the answer it's asking you for. So if I start with grams and want to get to molecules, what is the process that I'm going to use here? You can go directly from moles that we just solved in the previous part to molecules, and that is going to involve just recognizing that Avogadro's number is needed, and Avogadro's number is 6.022 times 10 to the 23rd. But I encourage you to also think about what this would look like if you strung it all together to go from grams directly to moles, rather than just thinking about it as, well, how do I start with moles and go to molecules? Now, that is a useful thing to think about because there are going to be times when you may be asked to solve for the number of molecules from the number of moles, but you're going to do that step anyways, even if we start with grams. So I'm going to show this from the standpoint of starting with grams and going all the way to molecules. And I'll point out, what step you would need if you were just going straight from moles to molecules. So this process is going to start off exactly the same as the previous process. So I'm leaving this so you can kind of see both. But notice that if we start with grams and we want to end up at molecules, we have to go to moles first. So our roadmap here is grams to moles and then moles to molecules. And remember, moles are a way of expressing the number of molecules. It's just a unit of molecules. So, we could have also, done like grams to dozens, to number of molecules. And I keep using this analogy that a mole is just like what we say when we say a dozen, right? We know 1 dozen means 12. We should also now know that 1 mole means 6.02 times 10 to the 23rd. It's just a number. It's a certain quantity of individual particles. So if after this first step of doing the 4.24 grams divided by the molar mass, we know that that gave us the moles of C6H6 because we just calculated it up here in part A. So we know once we type this first conversion factor in to our calculator that we've got moles. So to go from moles to molecules, you just multiply by Avogadro's number. So here is Avogadro's number again. And recognize here that this is given as a conversion factor, where we're recognizing that this is the number of molecules per 1 mole of this compound. And so I'm setting it up this way so that, again, my units are going to cancel out, and I'm going to end up with molecules. So when I work across here and I do 4.24 grams divided by the molar mass of 78.11184 and then multiply by Avogadro's number, 6.022 times 10 to the 23rd, I'm getting 3.27 times 10 to the 22 molecules of this compound. So again, I'll point out that grams to moles involved molar mass as a conversion factor. Moles to molecules involves Avogadro's number as a conversion factor. Okay, and note again that going from moles directly to molecules, if you wanted to do this, if you'd already calculated the number of moles, all we're doing here is basically multiplying by Avogadro's number to get from moles to molecules. So that is, something you could have done to calculate part B. But again, I'm challenging you guys to start with grams because you also need to know how to go from grams all the way to molecules, not just from moles to molecules. Okay, we're going to move on to the next one. So the next one is the total number of all atoms. Now, for this one, we want to recognize that we can tell from the formula, C6H6, that there are 6 carbons in this compound and there are 6 hydrogens in this compound, right? That would be 6 carbon atoms per molecule, 6 hydrogen atoms per molecule, but it's also 6 moles of carbon atoms per molecule per mole of the compound, and 6 moles of hydrogen atoms per mole of the compound. So note, those numbers can be used basically as conversion factors for either per molecule basis or per mole basis. So what I mean by that is we could write this as 6 carbon atoms per 1 molecule if we wanted to. Or we could write this as 6 moles of carbon per 1 mole of the C6H6, right? So either one, notice in either way, those are ratios of 6 to 1, which we could also write flipped, right? We could write it as 1 mole of the compound per 6 moles of carbon. So keep in mind, you can do either direction there. But notice that, the units here are kind of important because, again, if we're doing dimensional analysis, we want to make sure our units are going to cancel out appropriately. So notice that is for carbon that I just wrote, but you'd have the exact same thing for hydrogen. You could write 6 atoms of hydrogen for every 1 molecule, or you could write 6 moles of hydrogen atoms, basically, per 1 mole of C6H6. So this question, though, is asking for all atoms. So what I just did here for the 6 carbons and 6 hydrogens, that's actually going to be more important for this last problem down here where we're actually asked, how many carbon atoms are we going to need? So we're going to put a pin in that and come back to that later. But with the same kind of logic, let's also recognize that if we're talking about all atoms, then we're not distinguishing between carbon and hydrogen. So we're noting here that there are 12 atoms total, right? 6 carbons and 6 hydrogens adds up to 12 total atoms per 1 molecule, or there's 12 moles of atoms per 1 mole of the C6H6, right? So either one of those 2 conversion factors could be used. So if we want to solve this, again, going from grams to atoms, I'm going to show this full process, then this is what that is going to look like. Again, starting from grams, we kind of have a similar process to what we've done before, right? Grams goes to moles first. From moles, we can get to molecules. And from molecules, we can get to atoms. So again, notice that grams to moles requires the molar mass as a conversion factor. Moles to molecules requires Avogadro's number as a conversion factor. And now molecules to atoms is going to require the molecular formula, essentially. So, when you're going from molecules to number of atoms, you can get that conversion factor that you're going to need from just looking at the molecular formula and interpreting the molecular formula. So note here that doing this, I'm going to have 4.24 grams divided by the molar mass times Avogadro's number, and then I'm going to multiply by 12, because if I know the number of molecules, and there's 12 atoms per molecule, I'm really just multiplying this value I got from the last part by 12 atoms per molecule, right? Because I know that that's what I have in C6H6. Okay, so the answer you're going to get for that is 3.92 times 10 to the 23rd atoms, right? So that's the total number of atoms in this 4.24 grams of this C6H6. So again, note that this is how we do it if we start with grams and go the whole way through, and you need to know how to do that. But if you knew the number of molecules, this is also how we would do it to get to atoms from molecules. We would just multiply by 12 atoms per molecule. So moving on to this last part. Part D is very similar to Part C. We're simply going to change this last conversion factor because we don't want to know the total number of atoms. We want to know how many carbon atoms specifically are in this 4.24 grams. So we're going to change this approach slightly. And I'm going to get rid of all of this stuff here and just keep the, the information about carbon that we had, right? So remember that this is what we had figured out from the molecular formula, is that if there's 6 carbons per that molecule, then you can represent a conversion factor that relates the number of carbon atoms per molecule or the number of moles of carbon atoms per moles of the molecule. So again, starting from grams, very similar roadmap here, except the only difference from Part C is that we have carbon atoms instead of total atoms. And so notice that only change here is that we're multiplying by 6 now instead of multiplying by 12 like we did in the previous problem. So you could have gone from, all the way up here, the number of molecules down to carbon atoms by just multiplying by 6 atoms of carbon per 1 molecule. But make sure you recognize how to do this from grams as well. So our final answer here should be 1.96 times 10 to the 23rd carbon atoms. And the other thing you can note here is that it's exactly half of the total number of atoms.